Yeah.
And share my screen. Every once in a while I still forget something, but. You know, the biggest thing about this Zoom display is it's so small. The controls are so hard to like resize it. It's like too sensitive for it. There we go. Now you guys are nice and big. All right, so here we go. Let's go to this. First thing I think we need to do, and this would actually be a good review, is let's just talk about the ideal gas law and the first law of thermodynamics. So I would suggest turn to page, or chapter 3, the beginning of chapter 3, and let's just take a look a little bit about it. So we know that we have the ideal gas law, and the most, like, probably as the most standard form is PV equals MRT. Okay? But I really am not sure that I think that is a good way of dealing with it. So the other way would be PV equals N R star T. So in this case, right, this is the universal constant, gas constant, right? And we know that when we have N, which is the number of moles. Now remember, when I have the number of moles, a mole is a number of molecules that's in there. That's Avogadro's number. So that's the number of molecules. So those are the two ways that we look at it. So we know that MR is equal to NR star. So when we go N or R is equal to N over M times R star, what we're saying is that I can use the ideal gas constant if I know the number of molecules divided by the mass. But if I'm dividing it, right, this is like number of molecules per kilogram. If I think about this way, go to page 65. And it says that N is equal to little m over big M, and then I have the little m over here, R star. So I'm substituting N for this, right? That's what I'm doing. So I'm saying that the number, the mass divided by the weight of each molecule tells me the number of molecules. So given that, I get to cancel that out, and then I know that R is equal to R star over M. And that's just important because what we're saying is, what's the only thing about a gas I really need to know? I need to know the molecular weight because I should know what the ideal gas constant is. As a result, we now take this and we're like, okay, well, instead of using this, I'm going to go to PV equals RD. Times T. Times rho. Well, no. I'm just giving this. I'm going to, so if I know that I've got air, I know that the R that I want to use is this. And then I say, well, what is RD? RD is equal to R star divided by the apparent molecular weight of dry air. Right? And that's a number that we calculated by looking at the contributions of each gas, what each gas weighs, right? We came up with the apparent molecular weight. But because I want to go over this, I think it's easier if we go P equals rho RD times T. But we said that we can't just use T if we're using the ideal gas constant for dry air because that changes, the temperature might have some, the air might have some water vapor in it, so it's better to use this. So that's the form of the ideal gas law. that we want to use most frequently. P equals rho RdTV. So these are the ones that are kind of important. Now, in the module, didn't we have P? We had P equals NKT, where we talked about the Boltzmann constant. So I'm not going to worry about that for this class, but you understand that you get to some idea of the number of molecules times the ideal gas law for a molecule. That's what that one is. So I'm not going to worry about that, but that is in the book. So if you need to read that, and Allison, I don't think that's going to matter to you.
Yeah, because the stuff that we do for the PRD-TV is that he actually made us like derive to find TV.
Right. And that's fine, right? Because that's what we've done in class. So we did an entire lecture on that. So you could go back and get that one. Because that's what page 66 is all about. Now, keep in mind here, folks, that if I do this equals mass over volume, RdTV. So really, I'm sorry, I should have put mass in here. Do you guys see that? I should have put mass in here. What if I say this is 1? What am I basically saying?
1 over volume.
What do I call it when I say mass is 1?
Unit.
It's a unit mass. And if I call it per unit mass, then what I'm going to do is I'm going to want to say P equals
Alpha.
P alpha equals RdTV. And that's where this little guy alpha comes through. That is a specific volume. That's the volume of 1 kilogram of mass. Oh, hold on a second, guys.
We had a problem.
Uh-oh.
Who put the cap on the chimney?
You guys did.
We would never put that cap on the chimney. That's where the birds are coming from. That's the wrong cap. That is not a UL-listed cap for that. Yeah, somebody else put that cap on. We would never put that cap on that chimney. That's an air-cooled chimney. You have to have the right cap for that chimney.
Hold on a second.
Yeah, that's the wrong cap. So that's where the birds are coming from, see?
Okay, hold on a second, guys.
Mm-hmm.
I gotta do this here. Let me just pause the recording. Thank you.
Entropy.
389. Ugh. Oh well. So I'm back to recording. So anyway, let's just kind of review. So remember that this is P alpha.
Can you share your screen, please?
Oh, no. I want to share my screen. Am I recording? Yes, I'm recording.
Yes.
Okay, so there. So when you see that, this is what's going to be really important. And the reason we want to use that is, or the reason that this becomes significant is that this being a volume says that when I take something with a P dV or d alpha, what are you telling me this is? What is this?
PD alpha.
What is PD alpha?
Work?
That's a work term, right?
Work.
Because the work of a gas is expansion. So that we have an expansion going on, that is where that term comes from. So basically we're saying I can take the derivative of both sides. And when I take the derivative of both sides, I have to make some assumptions. One of the things that you want to think about is if I take the derivative of this side and the derivative of this side, the left side is easy. It becomes RD and the derivative of the temperature change. So it's saying if there's a temperature change, how much is that? Over here, because I have to use the product rule, I get PD alpha plus alpha dP. And that's where we get some of the multiple forms of the first law of thermodynamics when we start to deal with this. But I've just got to be careful of taking the product rule on this side. So whenever I use a problem, if I were using only the derivative of the ideal gas law, I've got to know a lot of things. And because these things are both derivatives, when I see this, here's what I'm thinking in my mind. Let me get rid of this for a second. I would think two different graphs. Okay, so I'd have two different graphs, and one of them would be P with V. And if I did that, if the volume gets bigger, what does the pressure become?
Smaller.
Okay, so I'm going to have this type of a graph.
It's an inverse relationship.
Right? It's going to be that kind of a graph. Then I'm going to have very small rectangles. And how wide are these rectangles?
dv.
dv.
dV, infinitely small dV. And then at that point, because it's infinitely small, it's only happening at a point, I have the pressure times the change in volume. If I reverse these two variables, I would have the same thing, but PdV. Now, where this comes important, and I'm okay with doing this because I was actually thinking about it the other day, go to page 94 in your book. And the key of the Carnot cycle on page 94 is found in figure 3.20. And notice that we have a pressure volume diagram, the same thing there. But we have two different terms on it. We have the adiabatic process and we have the isothermal process. So in an isothermal process, what do we know is true?
Aside from the obvious.
Well, no, I mean, say it though that way, Jim.
The temperature is constant.
Right? So if I look over here, I don't have a change in the temperature. When I have an isothermal process, I don't have a change in temperature. So it becomes very easy to work with an isothermal process because I know that I'm just changing the pressure and the volume, but I'm not changing the temperature. So let's take a look at a version of the first law of thermodynamics. So we get rid of this. Look at the first law of thermodynamics. And now I'm going to go back to the beginning of the book, or back to the beginning of the chapter, go a little bit further into it, into the first law, and realize that I have a bunch of ways of describing the first law of thermodynamics. Equation 3.34 is the first one, is that dq, and I'm going to change it a little bit, is dW plus du. This is internal energy. We said that internal energy is a function of temperature only. We said this is the work, and this is the heat. So it's an infinitely small amount of heat. We'll do an infinitely small amount of work and change the internal energy by an infinitely small amount. Right, right, and we would have to integrate, blah, blah, blah. But we know that dW is going to be P, and I'm just going to go straight to the alpha for a unit mass. I know dQ is there. And then over here we said, okay, well, this is fine. Again, if you look at page 73 in the book, you've got these same diagrams. There's your volume and your pressure change. These are the same things we've talked about. And we said that the next thing we talked about is the specific heat. So what we get to on page 75 is that equation 340 is that CV is the ratio of the internal energy change to the temperature change. Therefore, I can write in here as CV dt. And that's the idea of specific heats is what this is all about. So you got to understand that thing. Once we get here, now I've got something. So if I have an adiabatic process, the first thing is that this goes away, and then we manipulate this. This is where Poisson's equation is. But we're basically saying that PD alpha is equal to minus CV dt. So we know that. Let's go back and say, well, do you understand that's an adiabatic process? What if I had an isothermal process? Isothermal process, this term goes away. And now we see that the heat is what's causing an expansion. All the heat is not going to raise the temperature, it's causing an expansion. So in the Carnot engine, what we are going to talk about is a piston in a cylinder. And if you watched the mechanical, did you watch the Mechanical Universe? Please tell me you did. Jim, I know you did.
Yeah.
Okay, so that was really good, right? They talked about, let's get rid of all the bells and whistles of making an engine and go right down to it. So Hadley was the one who kind of perfected the engine. And then what was happening is they had a steam engine. They got how it worked. And what they wanted to do, the engineers wanted to make the steam engine more efficient. Get more mileage, get more power from some amount of fuel. So an engineer goes, how do I do this? Well, what's causing the problem? What's going against me? How can I simplify it? That's what an engineer does. But a scientist goes, well, let's theoretically figure this out. That's what Sadi Carnot did. He's like, let's look at the extremes. Let's find out what is the best engine possible. So when you go to this, you get this little piston, and you're going to push the piston in and out. Now, if I push the piston into this cylinder, what kind of a process is that? If I'm just pushing it in.
Compression.
Well, what kind of a process?
Oh. Adiabatic.
It's adiabatic, right?
Yeah.
Mm-hmm.
So go to page 94. And what they have here in that figure 3.19 is they've got the components of the ideal engine, this Carnot's ideal heat engine. And that little stand in the middle is an insulated stand. So when you put what this diagram is saying is when I put the piston on the stand, I'm not allowing for conduction. So there's no heat. That's why it's adiabatic. You push it in, it'll get warmer. Because it's adiabatic. So we look at the adiabatic form, 0 equals P d alpha plus CV dt. So I think it's pretty obvious if you measured this, you would be able to determine how much temperature you increase.
That's 0 equals PD alpha plus CDTV?
Yes. Now, look at second column on page 94 for the adiabatic transformation of the ideal gas from A to B. So we're solving this problem. So it says for the adiabatic transformation of the ideal gas from A to B, we have P at some point A times the volume. Now they're using volume. I could use alpha. Do you understand? It's not really any big of a difference. Is going to be equal to PB, BB, but it has this thing called gamma. And gamma is defined as the ratio. We've done gamma. Have we done gamma? Yeah. The ratio of CV to CP.
And that could be different based on whether it's atomic or diatomic.
Correct, right? So in a diatomic gas, like air is, we said this is a ratio of 3 to 5.
Right.
No. Is it CV over CP or CV over CP?
Said the same thing twice.
What is it supposed to be?
Specific heat to
The ratio of the specific heat and constant pressure. So it's, yeah, I'm sorry.
pressure to volume.
CP over CV, sorry. So we know that that's on diatomic gases 7 to 5, which is 1.4. And we know that from what it told us. We could kind of prove that out later, but this is what we know to be true. So we know that there's a thing about gamma. So why does gamma get in there? What's significant about gamma? And then it says, we invite the reader to prove in exercise 3.33. So let's go to exercise 3.33. And that's what we're going to start doing. We're going to start looking at how this works. Now, I'm going to go in here and I'm going to be a little bit, I think I can get rid of all of this. Oops. I can get rid of all this stuff.
Oh, 3.33.
Does everybody know where we're talking about then?
It's on page 104.
At page 104.
Yeah.
Mm-hmm.
This is about an adiabatic transformation. Now, before I go in to prove what they did, I want to take a look at what an adiabatic transformation is. We know, based on this equation, that, oh, that's a really big, that P d alpha equals minus CV dt. The minus sign makes sense because if it's doing work, where's the energy coming from to do the work?
The compression.
No. What's a work of a gas?
Expansion.
Expansion, right? When a gas, so I lift a gas, the first thing that happens is the pressure drops. The volume expands.
Mm-hmm.
And the gas cools. Why does it cool? Because expansion is work. Work requires energy. Energy comes from within. So when it's doing a positive work, the temperature will get colder, negative dT. Does that make sense? I mean, those are the basic ways that in all my classes, that's the way we discuss things. But the pressure goes down, the volume goes down. Do you understand that that is a problem? Because I don't know what the pressure is as the volume's going down. But I know that this equals P d alpha plus alpha dP, right?
Hmm?
And I can go, that's weird, it wrote over there. That's really weird. Oops. So P d alpha is going to be equal to the change in the pressure over my, sorry, that's terrible. What's wrong with me? The change in the pressure times alpha minus alpha times dP. And then I'm just going to do this. Now, the thing that I want to ask you and point out is, why is this important? Why do I like this? And there's a couple of reasons for this. Why is that an enjoyable thing?
Because maybe you can have something that you can integrate there.
Okay, do you agree that this is really easy to integrate? Right? This is a really easy thing to integrate. I integrated, it's P alpha. So I'm saying the pressure times the volume is whatever this is. Well, when I integrate it, what is this really becoming? The left-hand side.
Oh, it's part of the ideal gas law.
Right? So this is a good thing to have. The other thing that's important is when I've got these compressions and expansions, do you understand that the pressure and the volume are both changing? But I know that if I take whatever the pressure is times whatever the volume is, it's going to be equal to the ideal gas constant times the temperature. So before I even do that, go back to the diagram on page 94. So flip back for a second. So if I look at letters A and D, which is an isothermal process, I think it becomes obvious if P alpha equals RT, T is constant at both places. So I'm saying that PA alpha A is equal to, well, here, you know what, this might be an easier way if I do it nicely and neatly. Whoa.
That was neat.
Take it back.
Let me just do it this way. I'll do it a little bit larger so that it's nicer for James to see. The pressure at A times the volume at A is equal to the ideal gas constant times the temperature at A. But you agree that the temperature at A is the same thing as the temperature at D, right? But that tells me that that's equal to the pressure at D times the volume at D, which tells me what?
A is equal to D.
Right? That's pretty easy.
Right.
And that's what it says at the top of page 95. The same is true for B and C as it is in A and D. So are you getting that? I mean, that isothermal process should make sense. Because in an isothermal process, volume and pressure are inversely proportional. Pressure goes up, volume goes down.
Okay. Looking at that equation, since TA is equal to TD,
Right.
you can cross those out.
Right. I'm just saying.
And both the far left and the far right are equal to a constant.
Well, yeah, right. So
Okay.
therefore they're equal to each other.
Right.
And again, all I'm saying in this, and this is not to be confusing, this is the ideal gas law, and that's the ideal gas law. And all I know is that in an isothermal process, those two are the same.
And can be canceled.
So I'm just showing you why this is true.
Yeah.
Now let's get out of this.
So RTA also equals RTD as well.
Yeah.
Well, of course.
Of course.
Well, look, James, look at page 94, figure 3.20.
Yeah, I see what I did there.
So that's what I'm saying. You got to understand what that means on an isothermal process.
Let me rewrite that a bit better. I totally wrote that in a illegible manner. All right. That should be a bit easier to read.
But now in this one, it's saying, okay, well, wait a second. We're still trying to figure out this transformation with the gamma. So now, well, how do we get to that gamma? Let's go back to 3.33. It says combining 3.3, which I'm going to assume is the ideal gas law, and 341. And what do you think 341 is?
First law.
Okay, so that's what we've been working with here. And I'm still trying to figure out, what do I do with this? So if I integrated it, so can I integrate this? I would have to integrate this side. Now, what is the easy part of this? Well, the easy part of this is to say, well, I know how to integrate CVDT. So before I do that, before I even integrate, let me get rid of this because I want to show you how to get to this point. What do I do over here?
Divide by CV. No, wait a minute. I did this.
What do I not like to get? What do I not like on this side of the equation? What makes me not happy? I think that's an important question that you need to ask. What makes me unhappy over there? Allison, others, when I look at students, they don't see why this is a problem. So they never anticipate what they need to do because they don't know why it's a problem. So what's the problem on this side? Bruce, how would you answer that? Remember I said, I'm trying to integrate the left side, which means I need to integrate the right side. What's the problem on the right side?
Temperature and pressure are related?
No, I don't care because, right, and this is what I was trying to show you when I did this. I said you could just take the integration of both sides. This is easy. Integration of dt is t. But what's the problem over here? Can I integrate this guy? Can I integrate alpha dp? Okay, this is where you guys are getting hung up. This is this right now. If you're having a problem in anything that we do, this is the reason.
Alpha's volume, right? It's
Alpha
unit
volume.
volume.
It depends on pressure.
Pressure, yeah.
I can't do that. I don't know the function. Wait, we're saying it's a graph. What's that graphing? I don't know. So I can't do it if it's a function of it. But I know that P alpha equals RT. So alpha equals RT over P. Now what do I have? I have R T dP over P plus CV dt. I just substitute, get rid of alpha.
Should it be a minus CV dt?
Yes. Okay. Now, look what it says here. Show that for an adiabatic expansion, CV equals P d alpha plus alpha dP plus RP d alpha equals 0. Combine this last expression with 345. What's 345? Oh, look.
P equals CV plus R.
Okay.
So get rid of R in that equation, or substitute it.
Okay, so R becomes what? CP
Minus CV.
times the temperature, dP over P, minus CV dt. Now what? Look on page 104, top right, and we just want to show you that this is already stuff we've kind of done. So let me go, I can get rid of this. This little equation here that we talked about, CV times P d alpha plus alpha dP. I'm going to make a hunch. I'm not sure if this is what I want to do, but I'm going to try. Where did this come from? Where did we get this expression? Notice that they just have it plus that equals 0. Oh, hey, hold on a second, guys. Work through it a little bit, would you?
Mm-hmm.
What have you got here now? Am I sharing the screen? No.
No. You got rid of DT.
Do you see that I've got PD alphas on here? So CV plus R plus CV alpha dP equals 0. Can you see that? You know, when I did this, I said I had a hunch, and I don't know if I should have done that. I probably could have just done it this way.
I did it completely differently than you're going.
What was it? R P D alpha equals 0. So all I did was I took P D alpha, and I've got CV plus R. Right?
Yeah.
So what did you do, Jim?
Here, let me bring it up.
You want to share the screen?
Yeah, just hold on a sec. Let me get to it.
Because you did this the other day.
Uh,
I have to allow for your screen sharing.
no, that was a different problem. There, okay.
Let me get through this here. Hold on.
Okay. This is what? Oh, come on. Okay, here's what I did.
Okay.
Okay. There's the 3 equations. Differentiate 3, solve for PD alpha. And 3, 4, 1 DQ, it's adiabatic, so we can make that assumption. Then I rewrote and divided by CV. And that's 5 is kind of where you're at, but I've
Right,
already.
that's where you are at, right? When you're at 5, that's where we were.
Yeah, but I got rid of DT earlier in the game.
Okay.
And then a lot of algebra. And then here's where I bring in CP, or getting rid of R. More algebra.
Can you do me a favor?
Sure.
Can you email that to the class?
Can do.
But let me go back to the sharing. Hold on.
Okay, let me unshare. Stop sharing. Okay.
Okay, and let me do this. Let me erase this and go here. Let me show you a really cool little thing that I've got. So I'll write these down for you. I've got I went to the school to get my notes so that what color do you like reading in? Green? I like green. I just think that's a good color. So dq equals CV dt plus PD alpha. We say it's adiabatic. Therefore, CV dt equals minus P d alpha. But using the ideal gas law, P equals RT over alpha. So CV dt equals minus RT d alpha over alpha. Divide both sides through by T. And what does this start looking like? What is this very similar to? What should this look like, the derivation of? I mean, we did the same thing when we were doing Poisson's equation. Do you realize why Poisson's is so important to process through this? And Allison, this is the kind of thing that you're really good at working, and you do. Just keep working through that and seeing where I can substitute what you're doing. Now I like this. Why? Because when I integrate this, CV over R is a constant.
Yeah, you can pull out.
And then that's going to be the natural log of T equals minus the natural log of alpha. But what kind of an integral is this? And this is the trick that I don't think Jim, maybe you did, I can't remember. What kind of an integral is this when I just integrate both sides? What do we call this integral?
First order differential?
No. The integral is what? What are the two types of integrals?
It's indefinite.
It's indefinite. Right? We have definite integrals that have the limits,
Okay.
and then we have indefinite. Well,
Indefinite.
whenever you do that, when you integrate them, you should be saying plus a constant.
Mhm.
Plus a constant. Right? I mean, that's what you should be doing.
Right.
But the point is, if I have constants on both sides, that's just like another constant, right?
Mm-hmm.
So what I'm going to just saying at this is plus some constant. Done. It's the constant on both sides.
It's a constant of integration.
Uh-huh.
Okay. Oh,
Okay.
yes.
So are you seeing this?
Yes, I see where you're going. Yes.
So what do I want to do now?
Get rid of the natural log, so raise it to the eth.
Well, I can, but watch this trick. And this is truly a trick.
Log trick?
Oops. This is where, okay, so did you follow in here the calculus?
Yeah.
Did you follow the calculus? And the calculus was just integrating and making, it's an indefinite integral plus a constant. That's it. The rest of it is algebra. So I'm just saying because I can multiply through this and I get the exponent up there. So this is a rule of logs, which early in the class I said, you need to know your rules of logs. So you should have that written down someplace, study it, feel good about it, feel confident about that. Okay, now watch this. I'm going to get rid of this side. Which is just going to be a constant, different. It's a different constant. I multiply through by a constant. I just changed the value of a constant. Because all I really care about is that it's constant.
Couldn't you
But
only, the R over CP, couldn't that only apply to ln of t because it's because you're only multiplying CV over R times ln of t, right?
right.
But you can...
No, because I put it in here. See, over here it was, so watch this, Nick. Over
Yeah.
here, it was just associated with that, not with this. By
Okay.
putting it here, I'm now multiplying it through by that.
Okay, yeah, because you can do you can combine the logs, right?
Correct.
If you could see that. Okay, makes sense now.
Now, I don't like tea. I'm a coffee drinker. So I'm going to say P equals, or P alpha equals over R equals T. So I'm going to go, well, I'm using the ideal gas law here. I'm going to say, well, that's the natural log of P alpha over R plus the natural log of alpha to the R over CV is equal to some constant. And I'm just calling it prime so that you know it's different than the original one. Well, this is the natural log of P alpha minus the natural log of R plus the natural log of alpha over R over CV equals a constant.
Hmm.
Isn't this funny? But what's the natural log of R? It's just another constant. I bring it to the other side. It's just another constant because it is a constant. So now I have the natural log of P alpha times the natural log of alpha to the R over CV. And now here's another stupid trick. See, I did a lot of stupid tricks when I was young. How's that for a trick? You see what I did?
Hmm.
I just took this to alpha to the CV over CV. Because when I do that, I can now take the rule of natural logs and I say the natural log of P alpha to the CV plus R all over CV
Oh, that's.
equals a constant. But if I take e to both sides at this point, I get P alpha to the CV plus R over CV is equal to just another constant.
Right.
What am I on, 4? I don't know where I'm at.
You were at 2.
And so now you substitute for R, and you get CP over
And
CV.
now, right, so in here, CV plus R is CP.
Right.
So what this really becomes, and I'm running out of real estate, so I apologize. I don't have another blackboard. What I really get is this, P alpha to the CP over CV, which is equal to P alpha to the gamma,
Right.
equals a constant.
Constant. That's painful.
Okay, so what did I do? Is this the only way to solve this problem?
I did it differently.
Probably not.
Probably not. There's a ton of ways. Solving problems is about trying pathways and not getting in. Here's something you don't want to ever prove. 1 equals 1. Because that means you just cancel stuff out and you did something wrong. You want to continue finding paths. The only thing you need to be careful about is don't break any algebraic rules, because it's the algebra that messes people up. I mean, if you look here, it's the rules of logs. But in an adiabatic process, there's a lot of stuff going on, and what gets really hard is just knowing where to go. So that's why I asked Jim to send you his. He'll show you his. This is just another way to do that. And, you know, I'm not sure that this is the best way. It's probably not the cleanest way. Maybe there's some other way to do it. But the only way that you as a student will ever get better is to do paths and figure stuff out and go down wrong paths, and just be careful not to break rules.
I do appreciate the Packers colors, though, Paul.
Oh, good. Okay. What is their record this year?
They're 4-0.
Are they really?
Rodgers?
Is he doing good?
Yeah, he's doing really well this year. Really, really well.
So that's how this one kind of goes. At least there's a potential. Jim has another way of showing you that stuff. Just the key to this thing is when you say it's equal to a constant. Well, where does that constant come from? And the constant comes from the fact that it's not just the pressure times the density that's a constant. There's a relationship, Cp over Cv. And if you go back to where I left that last screen that I had, you will find that that's in there. And it's the transformation of these guys, heat resulting in temperature change, whether the pressure or the volume is constant, or the combination of the two is constant. Now you want crazy stuff? I'm telling you, I will show you a problem that I think is the hardest thing that I do in this entire chapter, because it took me forever to get there. But before we go there, I want you to go back to page 95. And just see that there is the transformation from C to D, which is the same thing as A to B. It's P volume to the gamma. But do you see that to the gamma controls how much the volume and pressure and the corresponding change in pressure will change when I'm changing the temperature? There's a relationship, and the relationship is based upon the specific heats of gases at constant pressure and at constant volume. That's what gamma is. It's the ratio of those. So there's a relationship to how a gas is going to change. Now here's the thing. It is not isothermal, so I'm giving it heat. Okay, so let's go back. Let me go back and just erase all this because you have it on video. Right, we have our first law of thermodynamics, right? That's the case. So I'm adding heat to a gas. I'm adding heat. Do you agree it's, oh, sorry, this is not dP. This is dt. Do you agree that some of that heat is going to making it warmer? And some of the heat is going to make it work.
It's going to be,
Have you ever thought why? I mean, here, let's imagine that I'm adding 8 joules of heat. Do you realize it could be 3 plus 5, or it could be 4 plus 4, or it could be 5 plus 3? So when I say in the first law of thermodynamics, I'm adding heat to a gas. It's going to do work, and it's going to raise the temperature. Well, what determines how much of that heat goes into work and how much of that heat goes into making it hotter? If you were an engineer and you wanted to make an engine, what do you want most?
Probably want to maximize the work as much
You
as
want
you
to
can.
maximize the work and minimize the rise in the temperature. But how do you do that? See, that's what Sadie Carter was trying to figure out. Well, I want a more efficient engine. So what's going to tell me, is there something that controls how much energy of this heat is going to work and how much is going to making it warmer? I don't think any of my students ever perceive that as a question they should be asking when I tell you heat goes into work plus change in temperature. But do you understand the significance of that concept?
yes.
Isn't that sort of like the base work for the whole heat death of the universe thing?
Well, you will see that as we go in through entropy. But that is the goal of this Carnot engine. How do I maximize the amount of work? Or is there some limit to how much work I can actually do? So he says, well, wait a second. I'm going to heat the gas, and I know it's going to expand. Well, what's telling me how much it expands when I heat the gas?
That PD alpha or D alpha.
Well, I guess the point is, right, there's molecules in here that I'm heating the gas, and those molecules, as they become more energetic, are going to change the volume. But in a parcel, the pressure is constant. So I know this pressure. And then the question is, well, how much of this heat relates to a volume change? Well, as we see, all those things are based upon the ratio of this. That's why we get alpha. That's why we get gamma. Is that there's a ratio of these things called specific heats. Now, do you agree that different gases have different specific heats?
Yes.
Mm-hmm.
You know, and it's related to the configuration of the molecule. We know a few things. We know the ratio is 7:5 for diatomic and 5:3 for monatomic. So where did these things come from? You know, and to be honest with you, I'm not exactly sure. I just know that that's what comes out of it because the ideal gas law plays a role in that as well. So now it says, now we have to look at the Carnot engine. So let's talk about how Carnot said, well, let's set this up. So let's see what he does. So go ahead and read that first paragraph for me, James, if you would, number 1 or number I, little I.
Yeah. Oh, I
We,
totally was on the wrong page. What page are we on?
94.
Carnot's cycle consists of taking the working substance in the cylinder through the following 4 operations that together constitute a reversible cyclic transformation. 1. The substance starts with temperature T2 at condition represented by A on the PV diagram in figure 3.20. The cylinder is placed on the stand S, and the working substance is compressed by increasing the downward force applied to the piston. Because heat can neither enter nor leave the working substance in the cylinder when it's on the stand, the working substance undergoes an adiabatic compression to the state represented by B in figure 3.2, in which its temperature has risen to T1.
So what we're doing is that first condition is A to B in the diagram. And where did I start? I started at some temperature. What temperature did I start at?
A.
You started at T2.
I started at temperature T2. So that's the colder of the two temperatures. And when I put the piston on the stand and I compress it adiabatically, I go to point B. Now, what has happened as I compress the piston? What three things have happened as I compressed the piston?
Well, the volume went down.
The volume goes down, right? The pressure goes up, and
Temperature increase.
the temperature increased from T2 to T1,
T1.
right? That's what's going on. And so you're making that little path from A to B. Okay, so you have that little path from A to B. The area underneath that curve is the work. Right? We've talked about that because the area underneath the curve is P D, I'll use D alpha. And what do I need to do? I need to integrate it. Now, I can't integrate it really easily because this is a bad function. But understood, if I integrate this, that becomes the total work. I'm not saying that I know how to do this mathematically, but I'm saying that's what it becomes because it's the area underneath this curve. I'm summing up an infinite number of P's and little rectangles dV's. The work is positive or negative?
Positive.
It has to be positive, right?
No, because remember, this is with respect to the gas in the cylinder. I'm compressing it, making it hotter. I'm compressing it, I'm making the volume less. That's a negative work. And what does it mean? The question is the gas doing work? No, work is being done by me.
Right.
So work is done to the gas because what did I have to do? I had to push the piston down. Okay, next, James, you're doing a good job. Go ahead and do point 2.
All right. 2. The cylinder is now placed on the warm reservoir H, from which it extracts a quantity of heat, Q1. During this process, the working substance expands isothermally at temperature T1 to point C in figure 3.2. During this process, the working substance does work by expanding against the force applied to the piston.
Now, this is where I got so hung up. Why does the heat go into the gas? It says it extracts a quantity of heat. Why is that happening?
Because the energy is conserved in the entire system. So the work that you were doing as the piston gets transferred to the gas.
No.
No.
I tell you, this caught me up. This was the difficult part. Why does heat get transferred to piston? So look, watch me. I take a piston, I push it down, and I warm it up.
Okay.
Now I put it on the heat source, heat supply. But what temperature is the heat source? What temperature is that heat source in the book?
I know they mentioned it somewhere.
T1, right?
T1.
That's
Right.
the temperature of the heat source. What temperature is your gas in the piston?
T2?
No, it was T2. You
Oh,
took
it was.
made it
Now
warmer.
now it's T1.
It's T1. If it's the same temperature, why is heat going into it? Conduction doesn't work if it's the same temperature. Conduction is a transfer of heat from warm to cold. The piston is still the same temperature. Why does heat go into it?
Goes into the piston?
Yep, why does it? Oh, into the gas in the cylinder is what we're saying.
Okay.
Because the red is showing me that no, look at the color in the figure. The red is insulated. Only the bottom of the piston and the top of the heat source are conductive. So it's the ability to conduct, but the temperatures are the same. Because look, if I push watch this now. If I push the piston in, did not put it on the heat source, and I let go of the piston, what will happen to it?
It's going to return.
Because the pressure inside is way more than the pressure outside.
Right.
So I push it in, and if I didn't do anything and I just let it go, it would go back out. It would be adiabatic expansion, and then I'd be doing nothing. I push it in, it goes back out. Push it in, goes back out. That's called an Aitken cycle. And if that's in that little handout that I gave you, that I'd like you to read again. We'll get to that later. But in this case, what happens is I put it onto the heat, and then if I let go, what will the piston start to do? It'll start to expand.
Right.
But if it's expanding, some of the energy of the molecules is being used for the expansion, and the temperature would go down. But as the temperature goes down, that's what allows heat transfer in.
Oh, okay. I see.
Oh, okay.
So heat is being transferred in from the environment.
Right.
Got it.
Now, in a hurricane, air comes into the hurricane. Do you agree, as it converges toward the center of the hurricane, the pressure is getting lower?
Mm-hmm.
Which means the air is doing what? The air is expanding.
Yeah.
The trajectory of parcels going into the center of a hurricane are going to allow those parcels to expand, and that would be cooling. But at the same time it's cooling, it's moving over warm water. So if it tries to cool by expansion, heat is flowing into the air from the warm water. And that's going to be an important thing. Okay, so now I've drawn in heat. Well, how much heat have I drawn in? Well, I've drawn in some amount Q. So now go to page 95. Look at the equation after 3.79. From B to C, so from B to C, the amount of heat, Q1 that they're calling, is where the volume goes from volume B to volume C of P times the change in the volume. Because what's constant? This is 0, right? This guy is 0. So the heat coming in, dQ, I'm going to integrate it, I get Q, actual total amount of heat. And then I'm like, well, how do I integrate this? Well, I don't know how to integrate this, but I can put the ideal gas law in here. P equals rho RT. So this becomes RT over V times dV. That makes me happy because R comes out. Why?
It's constant.
What about T?
It's going to have to be constant because it's isothermal.
Because it's isothermal. I'm drawing that heat in, and the heat will come in enough to compensate for the cooling of expansion. So that comes out. So that results in RT T times dV over V from VB to VC, which is nothing more than RT natural log of V integrated from VB to VC, which is an easy thing to do. But do you understand something here? That heat in this process is creating the volume change. So there's something to be said about that. You're like, oh, okay, well, wait a second. I guess that makes sense, right? I know what this is going to be when the temperature is held constant. Okay, now go to 3. James, go ahead and read 3.
Alrighty. The cylinder is returned to the non-conducting stand, and the working substance undergoes an adiabatic expansion along book website.
Isn't that hilarious? It should be along C to D. That is bad. Whoops, somebody missed that one.
Whew, that's a bad one.
So in other words, Sadie Carlo goes, the only way that I'm going to get an engine to work is if I have a book website. What the hell is a website, Sadie Carlo says. So right in that, it says from C to D.
Along C to D in figure 3.2 until the temperature falls to T2. Again, the working substance does work against the force applied to the piston.
Okay, so from B to C, do you agree that the volume is getting bigger? Which means the gas is doing what?
Expanding.
Which, yeah, but that means the gas is doing what?
Work.
Work.
The gas is doing work. So when I put that in here, that work is the area underneath the curve. So now, so this first area in green is work done to the gas. Now the yellow is the work done by the gas. Then it's going to go from C to D. So do you agree that will be more work done by the gas? Which I'm writing in yellow. Now you can kind of assume from here that I'm going to go back to D to A. And now watch this. Okay, so as I go from D to A, watch this. This is the green, because now from D to A, the volume is getting smaller. It's work done to the gas. So all of the green is this stuff. All of the yellow is this stuff. Do you understand that all the green and yellow cancel each other out? Work done to the gas, work done by the gas, except for what? What area is not canceled out? The area in that box. So that's the area in blue on figure 320. Well, what is the area in that box? That's your net work. Now, what would make the area in that box, that parallelogram, well, it's not a parallelogram, that quadrilateral, what would make that area bigger?
T1 and T2 being different values.
Yeah, if they were greater apart, wouldn't that make the area larger?
Mm-hmm.
Or if the volume was greater apart.
Right, so if you could if you could stretch it left to right,
Right.
right, that would do it. But the key thing is those temperatures going between temperature T1 and temperature T2. Okay, so this is where I started to get really confused. So I want you to listen to me. Now we'll look at the book. D to A. Look at me. I am compressing the piston. Okay? Let go when I'm at point, I'm sorry, rephrase that. A to B, I'm compressing the piston. I'm now at point B. I let go, what happens? It expands, and where do I end up?
Point C.
I end up at point C. So watch. Compress, I let go, I end up at point C. Now I go to point D, and what is the gas doing in that process? It's expanding adiabatically. Why? Why does it expand?
Pressure's gone down.
Well, the pressure does go down, but why would it go down?
Work is being applied
Because what-
against the piston, which is applying the pressure.
Now, think about this. Let's watch. A to B, expand, and then B to C, it comes back. But do you understand, when do I let go of the, when I let go of the piston, why does it come back?
Because the pressure inside the piston is greater than pressure outside the piston.
But do you understand that I need to put it from the stand of temperature change, the heat source, back to the insulating stand at just the right time so that it continues to compress? Because look, if I lifted it like this and then I let it go and it came all the way back, why would it continue to go back when I put it on the cooling stand? You have this worksheet called Nature's Descendancy. Actually, you know what? I can probably do it from here. Where's my blackboard? Man, has this weather been beautiful or what?
It's gorgeous.
Great.
So in the class notes, I have this. Where is it? Carnot engine reading. In order to understand, well, you know what I'm going to do? I'm going to open it here so I can zoom in a little bit bigger. In order to follow the engine through its cycle, we need to know some of the elementary properties of gases. Blah, 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 blah. Under these circumstances, the rise in pressure follows one of these curves, isotherms shown on the figure on the facing page. These isotherms are mathematically hyperbolic. So remember I said I don't know what the shape of this thing, well, it's a hyperbola. Because pressure is inversely proportional to the volume, which was established by Robert Boyle, which is an isothermal process. So that's Boyle's law. That's mid-17th century. So that's the 1600s. And then you throw it on an insulated surface, and that's adiabatic. The experiment observation is that during an adiabatic compression, the temperature of the gas rises. We shall see the atomic reason for this later, which we know. And throughout the chapter, we are keeping the world of appearances, not delving into mechanisms. The rise in temperature of the gas amplifies the rise in pressure that results from the confinement itself. So during an adiabatic compression, the pressure of a gas rises more sharply than during the isothermal compression, which should make sense because when I look at the first law of thermodynamics, that energy is going either into making it hotter, which would change the temperature, or making it higher pressure. And that's what they're saying here. And when you look at these are what the shapes of these things are. So the isotherms, let me erase all of this. I think I can. These isotherms, ooh, that's terrible, what happened? Are hyperbolas. The adiabats are different, but at least in diagram 320, that's pretty much the same thing. If the expansion is isothermal, then the pressure drops, blah, blah, blah. We already know this stuff. This is stuff we should know. I want to go through the important parts.
Is 320, is pressure a log scale?
No.
Okay.
Right, but that's the same thing as it is here, right? That's what this diagram is. It just looks a little different when I get to these areas way off to the right. So I just, you kind of got to keep that in mind. The initial state of the engine is represented by A in both illustrations. The hot source is in contact with the cylinder, blah, blah, blah. The piston is as far in as it will go, so the volume is small. So I push the piston all the way in. Hello, Amanda. The volume is small. The result of the high temperature and the combined volume, the pressure of the gas is high, which we know that. The first stage of the cycle is the expansion of the gas while the cylinder remains in contact with the hot source. The high pressure gas pushes the piston, and so the crank rotates. So this, in a car, your piston is going to generate a crank. That's the power stroke of the engine. This step is isothermal. So in order to overcome the tendency of the gas to cool as it expands, energy must flood from the hot source. This is what I was talking about with you guys. So the gas has a tendency to want to cool as it expands, but I compensate for that cooling by making heat go from hot to cold through conduction. So in other words, in a car, in your piston, what is the most important thing in the cylinder and the piston? I want a really good conducting material, metal. I want it to conduct because I need to get that heat transfer. Therefore, not only is this the power stroke, it also that sucks in energy, absorbs the heat from the hot source. Now, the designer of the engine could allow the crankshaft to continue to rotate and so return the piston to its initial position. So in other words, if you think of it as a cycle of a crankshaft, it goes up and it comes back down. So that you've got that expansion and compression. Then, if the compression is also isothermal, the gas will be restored to its initial state. Everything going back to it starts here. It starts at A, it goes around in the circle, and it comes back. I need to restore it back to its original position. That is what we mean as cyclical. It's got to go back to its original state. This would certainly fulfill one criterion. The cycle would be complete. The gas returned to its initial state, and the engine's ready to go again. We shall call this the Atkins cycle. Such a cycle is plainly useless, for in order to push the piston back to its starting position, exactly the same work needs to be done by the external, initially hopeful but now disappointed user, has been obtained from the engine in the power stroke. And I think this is how cars used to start. You turn the crank. And if you did that, you go back to original thing, but the car wouldn't run. You had to get something going on there. So it goes back and forth. Now, looking at this, I go from A to B to C to D back to A. And I've got nothing going on in there. So that's called the Atkins cycle, purposes. And that's what this looks like here. I go isothermally and isothermally. I keep going back and forth. What's the area inside, in between those two? See, this is all assuming that if this is an isotherm, do you understand that the compression and the expansion are happening at the same temperature, the same isotherm? What's the total work underneath this? Work going this way toward a higher volume is me doing work. The volume increasing is the gas doing work. What's the net work done?
0. It's the area under the curve.
And there's no area because it's the same isotherms.
Right.
So it says, and this is finally, I saw it once. This is it.
Is it that there's no area, or the area is identical because it's the same isotherm?
The area is the same. So
Right.
the total area in between the two are not. Remember, we need the area to be between two isotherms.
Right.
And now we've got
For there to be work.
The essential step in the Carnot cycle is therefore to break the thermal contact with the hot reservoir. Take it off the heat before the piston is fully withdrawn. Because if I do that and I take it off the heat source, what will the piston continue to do? It'll continue to go up. It will continue to expand. But since I took it off the heat source, now I have an expansion that's adiabatic.
All right. So the goal is to effectively remove it from the heated position while the piston is still going up.
And I want to set it
And that's at point D.
between T1, T2, and T1. I want to fix that time of removal at exactly the right place. This sentence here is the part that I've never seen in anything but this diagram. Every other textbook, this one included, every physics textbook, all says the same damn thing. And it never made sense to me until I realized, oh, I need to take it off so that it continues to expand adiabatically. So in other words, going from D to A, I'm heating the gas, it starts to expand, and then I need to take it off, and it will continue to expand till it meets the outside pressure. And in saying this, what we are really saying is that I need 4 strokes. 2 adiabatic and 2 isothermal. So let's take a look at this. At this point, we have begun to restore the gas to its initial position. The first restoration step involves pushing in the piston, doing work, and reducing the volume toward its initial value. This stage from C to D is performed with the gas in contact with the cold sink to ensure the compression relays as low as possible, and therefore that the work of compression is least.
1042, Paul.
What?
1042.
Oh, okay, we're almost done. As the piston moves in, the gas tends to heat, but the thermal contact with the cold sink ensures it remains at the same low temperatures. So if you think about this, when it's a really cold temperature, I don't have to do as much work. When it's warm, it takes a lot of work to compress the gas. Does that make sense? I am compressing a gas. It is resisting me. If the gas is super cold, how much is the resistance?
Little, because the
Little.
energy transfer is
If
going
it's
to be
hot,
great.
it's a lot of resistance. So what do I want? I want the compression of the gas to occur at really low temperatures.
Ideally, I believe it would be absolute zero, but it never will ever get
Yes,
that low.
and we'll get that as we go through it. Okay, so but the idea is that it will not give me much resistance because I'm providing the work. But if I let the gas do the expansion at high temperatures, then I'm going to get a lot of work back. I get more work back because it's expanding at high temperatures, and then I have to do to the gas because I want to compress it at low temperatures. Well, that's what happens in a hurricane. The air comes into the hurricane near the water at high temperatures. It's doing work. It's expanding. It then goes up, and then it comes down. It compresses at cold temperatures, and it doesn't take as much work, and I get net work. That work is what's stopping viscosity from the engine stopping. So I don't know how old engines worked on a car, but I'm assuming that you cranked the engine, and then you started it with a spark plug so that you'd start burning it. You had to provide the necessary work to get the engine going. That's why you cranked it. I don't know if you've ever seen videos where they're cranking a car. And you had to get the timing right. If you were too slow, if you were too fast, you didn't get that timing. Well, now what do you have in a new car is you start the pistons electronically because you have a battery. The battery is what gets the engine going. And then there's everything else is you still have a timing belt because if you're not timing the spark at the right time, you're blowing it up. They need to make sure that that spark, that heat, because that's the heat source, is the spark. The explosion of gasoline has to occur at the right time, or your engine is inefficient. But there is an extremely important point. Notice the importance of the cold sink. Without the cold sink, we have the primitive and useless Atkins cycle. In other words, if we don't take heat out, it's useless. As soon as we allow energy to be discarded into a cold sink, the lower the line of the indicator drops away from the upper, and the area becomes non-zero. The sequence is still cyclic, but now it's useful. However, the price we have to pay in order to generate work from the heat absorbed from the hot source is to throw some of the heat away. In other words, we are taking heat from the heat source, and we transfer that heat to the heat sink. We lose heat. It just is. This captures the essence of Carnot's view. And they talked about this caloric. We figured out a better way. So we need the cold source. So that's always the case. And we're going to talk a little bit more about this stuff on next week. Now, here's the thing that I want you to do. Look at page 95, equation 3.79. Remember how I said you guys have to figure out how to go down paths and become frustrated and then just keep trying?
Mm.
It says, combining the last four equations gives us this.
I hope you're ready for more pictures of that whiteboard on the carpet, Paul.
Do you see this thing, 3.79? I want you to try to figure that out. I want you to combine those last four equations and figure out those relationships. Do not spend more than an hour, but I guarantee you, you will probably take at least an hour to prove it. Good luck.
Cool.
I shall stop sharing and stop recording.